JW Physics. I'm Mr. McConley, and today we're going to talk about centripetal acceleration and centripetal force, things moving in circles. So I'm going to start out with a demonstration. I'm going to put some water in a bucket. This is a demonstration that a lot of you may have seen already, but it's quite a good demonstration. So I got water in a bucket, and then I can go like this, and I can spin the bucket, and only spill a little bit when I slow down. So, why can I do that? That's kind of what the lesson is about. So, just kind of center it up. Thank you. Let's talk about centripetal acceleration. Centripetal acceleration. I think it's easiest to understand if, by the way, if you want to know how to draw a perfect circle, here's how you do it, freehand. You look at the point that you start at, and you draw the circle without looking away from that point. That has nothing to do with the lesson, but I think it's important to know how to draw a circle. So you draw yourself a circle, and we're talking about centripetal acceleration. Now, if the bucket was, let's say the bucket was right here at this point, and it was spinning this way, clockwise, then the velocity of the bucket at that particular point, we'll call it V1, was heading that way. A moment later, the bucket was down here, and at that point, the velocity, which we call V2, was in this direction. A moment later, it could have been here. You kind of get the point, right? Well, what do you notice about the velocity? First of all, you need to notice that the velocity is always tangent to the circle. These are tangent, math term, tangent to the circle. And you'll also notice that the velocity continually changes direction, but which way generally is it always moving? Like if you go from this picture to this picture, you can see that this has tipped inward, tipped inward, tipped inward. These velocities are always changing inward. That's important because the word centripetal means center seeking. Center seeking acceleration. So what's happening is your velocities are always changing towards the inside of the circle, and that's where centripetal, the word, comes from. Now, let's get to the bottom line. The acceleration, when you're talking about in a circle, and that C, some people think, oh, that means circle. It actually means centripetal, but if you think of it as circle, you're still going to be right. So, centripetal acceleration is V squared over R. This is in the reference table. V being the velocity you're traveling, R being the radius of the circle. And that's in meters. And so this will find you the centripetal acceleration. But sometimes you don't have the velocity. So what if you're not given the velocity? How do you actually find the velocity? Well, let's go back to thinking about old school. The average velocity was distance divided by time. Got it. What's the distance if you're going around a circle? How do you figure out distance around a circle? We call that circumference, right? So how do you figure that out? Well, if you remember your math, a lot of blank faces. What? 2 pi r. Okay? I didn't hear it, Hannah. I'll give you credit if I heard it. So anyway, the distance around the circle is 2 pi r. So basically, although this is not in the reference table, if you're trying to figure out the velocity, you just need to know how much time it took to go around. And actually, they changed that letter instead of a t. Most people write a tau, which means period. If you remember from pendulums, this means period. And period just means the time for one complete cycle. So we got the period, 2 pi r on the top, that'll give us the velocity. Now we're able to do the acceleration, and just to take it one more step, you can also find the centripetal force. And the centripetal force is very easy to remember because it's just mass times centripetal acceleration. This old equation you've become very familiar with when you're doing F-net problems. So you can take your acceleration, found this way. If you need to find the velocity, you can find it this way. And you can tie all these things in together. So, the velocity is changing towards the center. So if we go back to my picture, I'm going to erase these red arrows for a second because I don't want to confuse things. If I go back to my picture, what direction is the acceleration? I said center seeking. So if you drew it as a vector, the acceleration would be pointed towards the middle. And you know from Newton's laws that whatever direction the acceleration is, the force, complete my sentence, whatever direction the acceleration is, the force is in the same direction. So, if you drew the acceleration this way, and you wanted to draw the force, you could also draw it as a center-seeking force, a centripetal force, a centripetal acceleration. Forces and accelerations have to be in the same direction. So tying it back into the original demo, this bucket of water, as I spun it around, the velocity was constantly changing direction, therefore it was accelerating, but what's amazing to think about is it was accelerating, however, what was true about the speed of the bucket? Constant speed. So when something's moving in a circle like this, you were at a constant speed, but at changing velocity, because velocity also depends on direction, right? This is kind of a key concept with centripetal things. You're going at a constant speed, but you're changing your velocity. And notice that the acceleration and the force are inward, so you are pulling the water inward, but the water wants to remain going straight. This water, if given a choice, if I was spinning the bucket and the bucket had a hole in it, the water would try to squirt out the side, because it wants to keep going straight. But since the bucket is containing the water, it's trapping it and it's pulling it around in a circle. So that's it for centripetal forces and centripetal acceleration.